team of presenters with you?
Oh, no, I'm the only one.
Okay.
They are my co-authors. Alexis and Monica are my co-authors.
Oh,
But
okay,
they're not
all right.
here. Only one is me, and I'm presenting.
Okay.
Yeah.
Good afternoon, everybody. David Kutas is going to present on extraterrestrial drilling operations, fundamental research. Thank you.
Thank you so much for your attention, and it's an honor to stand here and just let's get started. So, I'm a recent graduate from Universität Leoben, Austria, and with my co-authors, we started the research because we think it's a really interesting and really inspiring domain to talk about. And since we were majors in drilling engineering from Austria, that's our field where we could contribute to going to Mars and to sustain life over there. And so my agenda for the next couple of minutes will be about an introduction where I'm talking about the scope of this research, the motivations, the possible added value by the research we conducted, and the position of the petroleum industry, which involves deeply in this field, we believe. The second part will be about general considerations about Mars, so to ground why drilling is important, and to ground these problems, what we are facing currently, why we would like to, if we would like to conduct drilling operations on Mars or any other extraterrestrial environments. The third point I'm going to talk about is that I'd like to give you a broad and general overview on the drilling principles, what we are doing, because that can help later on, I think, everyone to design new processes, new methods, how drilling could be done. And based on these foundings, on this grounding of the drilling operations, I'm going to talk about some considerations, problems, and possible solutions, how we could overcome these issues. And in the last step, I give a little bit of a summary. So the motivations is that self-sustaining communes on Mars later on, if we go there, will need relatively cheap and easily accessible energy. And one ways to do this, we believe, is can be geothermal energy. And also that we don't know that what's exactly located in the subsurface regions of Mars. It also would be very beneficial to get some more information about the deeper subsurface areas. So the information extraction is also a very important part of this drilling operations. And nowadays we can state that drilling is the most advanced and most thoroughly worked out, and the most innovation goes in the petroleum industry, because we are drilling a lot. We are drilling deep wells all over Earth, and we are sometimes seen as a devil industry, so the evil ones, but it's not actually true. It's a necessary thing on Earth, because it's a relatively easily accessible energy, and so that's why humans, or so mankind, came to this, that we need to use this to be able to achieve greater causes, like going to Mars. And so despite of these advanced methods, what we are using in the petroleum industry, or more specifically in the drilling industry, is that there is no intention to focus on innovation. It's not so important for the petroleum industry to go into more innovative solutions. And then so the goal of this research is also to fuel imagination in the petroleum industry, to collaborate with the aerospace industry to get these research done, which would need to be done. That's our belief. So the scope of this research is to cover the most important terms in drilling engineering and to ground this research for later on. And the added value can be that it fuels research both in the petroleum and aerospace industries. And this is an outlier, a little bit of an outlier slide here, because the position of the petroleum industry shows us that there is an incredible tension in there, and that causes a lot of fluctuations, how the petroleum industry should be or could be kept as it is, or it should be changed, or we should move to another energy source. And there are a lot of debates about this. And there are a lot of changes going on. Starting from here with, for instance, renewable energy sources. And the tension in the petroleum industry comes from a number of sources. There is a general direction of the petroleum changes from east to west to east. So there is an enormous change in there. And there is also the technology changes. So for example, hydraulic fracturing gives us more opportunities to access more information and more thoroughly these energy sources, and to fight. And there is also a tension coming from that. A lot of parties are fighting to keep the status quo, to keep this industry risk-driven instead of cost-driven. And however, despite all these tensions, there are incredible resources in this industry, because it's one of the biggest industries in the world. So there are a lot of bright minds working on problems to solve, and there are also financial and other sources which could also help the aerospace industry to ground this Mars research too. So there are possible ways forward, and we believe that sustainability, both in the petroleum industry and in the aerospace industry, could be done if we could combine these two interests and two ways of thinking and two industries to fuel research and help each other. And so, coming to the more specific scientific side of it, there are some considerations regarding Mars and from geological point of view. So Mars is inner core is composed of iron and nickel mostly. The most predominant components of Mars are mantle and silicate minerals. So there is not much of a difference if we would like to drill more deeper wells on Mars compared to Earth. But there are some general characteristics of Mars which makes it really hard with the normal drilling procedures what we have on Earth. One of that is the gravity, so it's lower. It's about 35%. You must know more about this than me, actually. And so, and also the atmospheric pressure is much lower. I will come to this, that why it is a huge problem for us. And there are some other considerations that, for instance, Mars no longer has a magnetic field that would act as a shield. And also the thin atmosphere is very volatile, or it's very difficult to trap any heat provided by the sun, and so on and so on. I will specify this a little bit later on. From geophysical point of view, is that the first would be to get more information about the subsurface regions of Mars, and that's should be done through more thoroughly designed geophysical methods and information acquirement methods. And that could be done by recording seismic activities, with conducting gravimetry measurements, geomagnetism measurements, and radiometries. And coming to the drilling principles, what's the most important here is that we chose to go, there are a lot of methods for conducting drilling engineering. Drilling works also on Earth, not only on Mars, but because the petroleum industry has the most complex method applying in it, then we chose to go with this. This is not surely right, but this is a good starting point for us. And why we chose this, there are a number of reasons. As I mentioned earlier, that we have the most experience accumulated drilling wells. And also we are the most actively developing and searching for mineral resources, and also equipment-wise. The most active in the field of research and equipment. Most complex concepts are utilized here. And so that's why we chose this. And then the definitions, and there are some definitions which we need to go through to understand in the couple of following parts. So the definitions are, when we would like to drill, there are a couple of limitations or design factors come into the view. The first one is the fracture gradient. which is this line. The fracture gradient is that actually that's the pressure where the rock breaks when we try to drill. So that's our upper line, which limits us. Then there is a lower line that's called the pore pressure. The pore pressure is we can state that that's a hydrostatic pressure, equals with the hydrostatic pressure in a given depth. And that gives us a window here in this region, what we can use to drill our well. So if we go lower this line and we start to drill, then we're going to get into troubles. If we go higher than this, then we are also going to get into trouble. So that gives us the drillability window, a so-called drillability window. And to be able to stand between these lines, we need a so-called drilling mud. A drilling mud is like a weighted fluid material, so we can deepen our well. And I will come to this too, that what are the main problems with this. To be able to reach the depths, we need a drill string, a weight and bit, and a rate of penetration. And when we actually drill, we accumulate cuttings. These cuttings needs to be transported to surface, and that's what we are also using the drilling mud. And then when the borehole is deepened down, we need to case that hole to be able to stop collapse and to stop the exposure of the drilled formations to the changed ambient conditions. And when it's also done, we also need cementing. Cementing is a layer between the casing and the formation, and that helps us to keep for long-term, so to keep the well also long-term. And so in the oil field, there are drilling rigs, and these drilling rigs are rather simple tools, what we are using, and they can essentially, so the best way is to understand that how the whole drilling process goes on is to walk through this whole process. And then, so let's start it. The oil field drilling rig is capable to execute the following simple task. So it can lift the drill string, it can rotate the drill string, and pump through the drill string. The pumping through means that the mud can be taken into the wellbore through the drill string, and then it can be circulated out later on. So let's start with the power system. So we need power to power our drill string and our top drive to rotate the string. So, and there are some electric motors or diesel engines. Mostly in the petroleum industry, diesel engines are used. And then we come to the circulation system. When we prepare mud in the mud tanks, then mud pumps are pumping out the mud here in this line. The mud goes up there, and we pump into this line. And then there are some other tools what we are using. So for instance, the drilling mast that's one, and the drawworks, which moves the drill line, the crone block, the traveling block, which is this one. So there are some auxiliary equipment what we need to use to achieve this rotation, lift, and pumping. But the most important thing, maybe the most important thing, is the so-called top drive. So this is able to rotate and lower and move the drill string. And so the drill string consists of a couple of drill pipes, and in the lower part also consists so-called bottom hole assembly. The bottom hole assembly is a tension. It is capable to withstand compressional forces. The drill string cannot do that. And so when it's done, the last part of this is the drill bit. The drill bit is actually the tool which penetrates the rocks and breaks the rocks, and that's also the tool where the drilling mud is exiting and comes back and enables us to transmit the mud into the annular space and come back with our mud to surface with the cuttings accumulated in it. And when we come to the surface, there are a couple of other very important materials, and that's the stationary subsystem, I call it, and that's the wellhead, and we have a blowout preventer. So when we cannot stay in between the two lines, we still can do some preventive actions to stop a catastrophic consequence of the operations, and that's what the BOP therefore. And circulation system is coming to the page again. So when the cuttings are accumulated in the drilling mud and they are returned back here to the shale shakers, and the shale shakers are taking out the cuttings from the mud, and so the mud can be used again to start the process of drilling again. And so there are a couple of hazards which we can also face on Mars, because we don't know what's under the surface right now. So there are fluid influxes, and then there are also wellbore stability issues. Most of the cases, wellbore stability issues are expected to happen on Mars too. And there are also some other things. So for instance, sticking, mechanical and differential sticking. This means that the borehole closes, the borehole closures, and then we're stuck there with our drill string, and we lose and possibly we have the possibility to lose the whole drill string. So our whole operations just fails. And there we also need to mention here that there are some alternative and new oil field technologies which could help us to achieve more efficient drilling. And so there are the coiled tubing drilling and casing drilling, managed pressure drilling, and the plasma drill bit. And so I come to the problems, and then I'm going to mention these alternative oil field technologies which could help us. So Mars is a harsh environment, but nothing harsher than, for instance, Siberia, where they are also drilling, and the temperature there can go down to -40 in the wintertime, and also come back to +40 in the summertime. So the materials there also needs to withstand a wide range of application ranges. So, but the biggest problem is not the temperature, but the pressure. So when we would have a fluid that could evaporate and all this kind of stuff, so the drilling mud can be hardly used. And also because the Martian rocks have lower, so they were formed in a lower gravitational environment, the drillability window would also go down, so in a lower region. That would cause us that we could have more instability and stuff like that. So because of the low fracture pressure, when the rocks are drilled, they are more likely to be unstable. However, the drillability window can be the same, just stays in the lower region compared to Earth. So that's not a too big deal. But so we could use a couple of technologies to overcome these issues. And one is casing drilling. So casing drilling means that we could use, instead of a drill string, a casing, and put underneath the casing our drill bit, and then we could use this. So then we would reduce the exposure time of the given formation, what we are actually drilling. So this is an accepted method in the petroleum industry, but not many companies are uses that. And managed pressure drilling could be also used, which would mean that our so far atmospheric system is not atmospheric, so ambient anymore. So we could close it down, and then we could apply back pressure to stay again in that two lines, what I mentioned earlier. And also we could precisely monitor the conditions downhole. Another problem is the cementing. We use cement to set the casing in there, in the wellbore. And then, so the cement sets on ambient conditions. It needs a certain time to set, but it is expected that on Mars, because of the lower temperatures, it would even not set or would take a lot of time to set. So, and also the preparation of cementing would take a lot of time or would not be possible. So the efficient cementing would be needed to be done in case of regulated ambient conditions. And that's makes up another groups of problems. For the energy sources, we have three considerations. We try to walk into this, that what we could use to replace these diesel engines I mentioned earlier. And then the first one is that solar energy, which came to our mind. That's what we were seeing from Mars rovers. And then we figured out that there is nuclear energy. Nuclear energy is not a new consideration. For instance, the Russian had the Topaz in space, and also During the Apollo program, we figured out that there was the SNAP auxiliary nuclear power in space. And then also there is another consideration for fuel cells. And of course, sorry, I forgot to mention that Curiosity, now the Mars rover also has an RTG. Then we were trying to come to this one and then decide which could be the most useful, robust, and most reliable solution. And of course, nuclear turned out to be the most robust and most serious solution for us because we need enormous amount of energy to conduct the drilling operations. So the conclusion of this, that nuclear energy seems to be the most adequate solution. And so coming to the next problem, the fluid system in conventional drilling. And then there is a fluid system in conventional drilling that we are using. This can be either a liquid, gaseous, or a foam system, but mostly it's a liquid system with water-based mud or oil-based mud. And the most important thing here is that when we are designing our fluid system, we need to create a rheological model. This rheological model means that we need to, with the annular velocity here, we need to overcome the cutting slip velocity. If we're able to do this, then the accumulated cuttings in the wellbore, which are created by the drilling process, can be taken to the surface, so the drilling process can commence, and then we can drill further down. If this is not possible, then we're gonna have, for instance, sticking, or our reduction of rate of penetration will happen. Also, the annular pressure losses will increase. There will be a lot of problems with the wellbore stability, as I just mentioned, and there will be also increased downhole vibration problems. The biggest problems with this is not even that we have lower pressure on Mars, so that the fluid system would evaporate, but to take a mud from Earth to Mars seems to be impossible because of payload limitations, because of limited resources. So what we would need for this is in situ research utilization. And what we think that because of the lower gravitational constant, and also because we have an unlimited source of CO2 on Mars, this could be also used as a gaseous system there with helical drill string design to take our cuttings up back to surface. And also the application of managed pressure drilling. Weight on bit is another consideration. So to be able to drill a well, we need to apply weight on the bit to be able to commence and to drill. Without having weight on the bit, the drilling operations would be slow or even cannot progress. The problems with this, that there is a certain buoyancy factor, but this buoyancy factor is unknown because our fluid system is unknown or not yet decided. And also because of the lower gravitational constant, the drill pipe has a nominal weight on Earth, but this will be lower in Mars. So either we would use a higher nominal weight drill pipe, but that would also cause that the transportation or the payload limitations come into play. But then we figured out, because the drillability window is also lower, so we need less power to break those rocks, the nowadays used drill pipes or methods or calculations are adequate for Mars too. So the considerations with this is that lower strength formations expected to require lower weight on bit, as just mentioned. And there are some other wild expectations from us that, for instance, the plasma drill bit, what we are hearing a lot about in the petroleum industry, the drilling process could be conducted without the need of weight on bit, drill string, rotation, and also the drilling fluid. So plasma drill bit is a really interesting field where we should think more on that. Coiled tubing drilling technology would enable us a more simple design and the ability to combine this with other technologies, for instance, plasma drill bit or managed pressure drilling. And another very important consideration is coring. So how we could have more, let's say, information about the subsurface regions. And we do this the same in the petroleum industry. we need information because of, for instance, permeability analysis, porosity analysis, rock strength testing, and paleontological dating. And that's particularly important for Mars, from proving that there is life or no life. And so nowadays in the petroleum industry, it's done in a very complex manner. So for instance, when we drill down to a certain depth, then we take our whole drill string out, then we run into the hole with another drill string, which has an outer and an inner barrel. And then we drop a ball, so we deviate the flow of the mud into our, out of the outer barrel, and then we start drilling again. When we do this, a certain amount of formation comes into the inner barrel, and then we try to pull up, and that breaks. Then it breaks the formation here, and then we can come up with that certain core up to the surface to measure its details, its properties. But this is a very complex tool package, and the replacement of drill string assembly in Martian conditions would cause a lot of problems, and it's an enormous problem there. And so the consideration is that we should have the application of more advanced automation and robotic solutions in the drilling industry, which would require less manual intervention to working processes. And the last group of problems is, of course, the most biggest hurdle. What we see is that now in the cargo requirements regarding drilling equipment transport from Earth to Mars would need hundreds of tons of magnitude, would be ranging in the hundreds of tons of magnitude. But as we can see now, that it would be enormous thing if we could even take to Mars a couple of tons. But there is a consideration here that the rate of development in this field is projecting that this will change soon, or this can be changed pretty easily. And so coming to the summary, the situation in the petroleum industry seems to be unsustainable for the long term, but it's also, we see that it's unsustainable in the aerospace industry. So we have been on Moon almost 50 years ago, but we are not on Mars, and we are not expecting to be there in 20 years. And so most of the already developed measurement systems, measurement methods for geophysical basic considerations are already there. We covered the drilling principles. We see a lot of problems, but these problems can be overcome. And the next one is that these drilling characteristics or design factors, we have identified a couple of broad domains where we could work on, and those are automation and robotics, advanced and alternative drilling technologies, advanced energy sources, and also logistic solutions. And come to my last point is that we would like to not let these things sink into oblivion by just finishing this research. So we opened up a web application called LineSep, where we are collecting considerations, ideas regarding space drilling as for now. And then from that one, we would like to go into more thoroughly worked out considerations. And also based on your response, we would like to see that where we are lacking knowledge and where we could go to do this better. So thank you so much for your attention.
A generation ago, I read a book by Thomas Gold, a geophysicist. Are you familiar with his work on the hot, deep biosphere and the locating petroleum reserves in non-sedimentary formations?
Not yet, but thank you so much for the idea. I need to talk with you after that to write down the name and learn more about it.
Okay, we'll work something together.
Yeah.
I imagine there's many variables driving the power, but for a typical, you mentioned diesel machines, for a typical bore diameter and feed rate, what are the power requirements for a drill?
That's like, for instance, nowadays in the petroleum industry, drilling rigs which are capable to drill down to 50,000 feet with 8.5 inches diameter holes. They need like 3 or 4 drilling diesel engines with 1,500 horsepower. And those machines are working 0 to 24 hours a day. And so there's enormous amount of energy what we need, even if we would go lower borehole diameters or less depth.
Is your intent on Mars for geothermal venting type activity, or?
We surely believe that geothermal energy, not only on Mars but also on Earth, could be more thoroughly utilized, and also with the application of CO2, the options for geothermal energy, we think it's one of the viable sources. But it's also important that we just considered this, but we would need to go more into this to surely state that geothermal energy is a viable source on Mars too.
You have questions?
One more question.
Here we go.
Hi, I don't know a great deal about drilling industry, but it's my understanding that most techniques we use require a great deal of water because water is easy to get on the Earth. We don't know how much is on Mars. There may be quite a bit, but there may be in short supply. Do some of these techniques use not very much liquid?
Actually, so we need most of the liquid, or in general in the petroleum industry, we use a vast amount of liquids for the drilling mud. But this drilling mud can also be gaseous or foam, which would need much less liquids. So, for instance, water.
You could really do this with, how deep a well can you drill with a gaseous system, do you think?
That's really much depends on many properties, but as the gravitational constant is also lower on Mars, with the helical drilling design, we also believe that thousands of feet can be achieved.
Okay, we're out of time, and thank you.
Thank you so much for your attention. Here.
This is the click-through, I believe, and then, oh no, the arrows.
This advances the slide, this goes black, and that's a laser pointer.
Well, what does the center button do?
Don't touch it, don't find out, right?
Yeah, launches a nuclear weapon. Our next speaker is Kurt Chankaya, and he'll be speaking on the human factor, manned or unmanned. Some thoughts on mission resilience.
There you
Thank
go.
Kurt.
Let people settle for a sec. This is a disheartening room to speak in because it doesn't matter how many people are here, it still looks empty, you know?